This episode is brought to you by WeatherGuard Lightning Tech. At WeatherGuard, we make lightning protection easy. If your wind turbines are due for maintenance or repairs, install our Strike Tape Retrofit LPS upgrade at the same time. A Strike Tape installation is the quick, easy solution that provides a dramatic, long-lasting boost to the factory lightning protection system. Forward-thinking wind site owners install Strike Tape today to increase uptime tomorrow. Learn more in the show notes of today's podcast. Welcome back. I'm Dan Blewett.
I'm Alan Hall.
And I'm Rosemary Barnes.
And this is the UPTIME podcast, bringing you the latest in wind energy tech, news, and policy. All right, welcome back to the UPTIME Wind Energy Podcast. I'm Dan Blewett. On today's show, first we're going to chat a little bit about some big news from MingYang. They've released a 16 megawatt offshore turbine that they're going to hope is going to be in service in a couple years. So we'll talk about some of the thing is gigantic and obviously now displaces the Halley 8X and the Siemens Gamesa, their top turbines as far as size. We'll talk at length about gearboxes today, some about gearbox failures, also an interesting wear debris monitoring system from Poseidon. We'll talk a little bit about what we can do to make those gearbox maintenance periods, extend a little bit longer. And then in our third segment today, we're going to talk about hydrogen. Rosemary's got a ton of stuff she wants to share, and we're going to chat through how green is blue hydrogen. We'll talk through Liebrich's hydrogen ladder and some interesting hot brick technology that could be used to store energy, not really hydrogen related, but also just energy storage related. Before we get going, be sure to subscribe in the show notes below to UPTIME Tech News. That's our weekly newsletter and podcast update. So if you want to stay abreast of everything wind energy, definitely sign up for that. You'll find it in the show notes here in YouTube, Spotify, Stitcher, or wherever you listen. And obviously our co-host, Rosemary, has a great YouTube channel, so you'll find links to that there as well. So let's get going. Rosemary, I'll kick this to you. So MingYang has a 16 megawatt offshore turbine, the MySE 160-242. So it will sweep a 242 meter area. That's the rotor diameter, 118 meter long blades. And that's going to be a 46,000 square meter swept area. So, Rosemary, what are some of the challenges as these continue to get bigger and bigger and bigger? Is there ever going to be a cap on turbine size?
It's so funny because that's like the question that everyone's been talking about, forever, as far as I can tell. I know when I was working at LM, if someone had a 10-year or a 25-year working anniversary, we'd all have cake in the canteen, and it was like followed the same pattern every time. They'd give a speech and they'd say, when I started, wind turbine blades were 12 meters long or whatever, something like that, and we all wondered how long they could get, and we were pretty sure 20 meters was the limit. Everyone had this story like that from when they started. And I started a lot more recently. And I guess for me, I think it was in the 80s, the longest blade in the world. And people were like, could it get above 100 meters? I guess in theory it could, but would you ever? And it's kind of funny because of course there's no hard limit. I don't think that you could realistically make a, kilometer long blade. But I bet if there was like a real incentive to, you probably could. But the thing is that, as you scale something up, the actual structural considerations are not in favor of getting bigger and bigger because you double the power increases with the square of the length, but then the mass of the materials increases with like the cube because it's three-dimensional. So the blades of a bigger wind turbine are more expensive for the amount of energy you get, but it's all the other savings in other parts of the turbine. So you'll see, obviously for offshore, it's really expensive to run those cables out to the turbine, and it doesn't matter so much if it's a cable for a 10 megawatt turbine or for a 16 megawatt cable. And so, basically it's just economics. And at some point, the optimization is constantly changing. That's why turbines are getting bigger. At the moment, the size of turbines, that's the optimal size. And then when that changes, then you get a bigger turbine. So yeah, I've got no answer to when it will stop. I think that any guess you make is just definitely going to be proven wrong. So yeah, another bigger one. That's all I can say.
That's fair. Well, I remember hearing back in the day, and this, I don't know if this is true or not, that Godzilla it was King Kong. That King Kong couldn't have existed because if an ape was that big that his bones couldn't support his weight, essentially. I don't know if that was correct, but I feel like I read that. I mean, could that be kind of what you're talking about to an extent? Like at some point, might the nacelle and the blades up top just be too much for a reasonable sized tower?
Yeah, it just costs more.
Right. It is like the dinosaur experiment where dinosaurs got to a certain stage and they couldn't get any bigger because their structure couldn't handle it. So they stopped.
So I was right. That's
growing.
It's good.
Yeah. And that's the same thing's going to happen it's already happened in airplanes, so to speak, and it's going to happen in wind turbines. The question is, at what point does it become painful? And until you push engineers and materials to the point it becomes painful, they're going to continue to make them bigger and bigger and bigger. Now, are we getting close to that number now? I think we are. I think my gut tells me 200 meters is about, when you talk about ship sizes and things like that, 200 meters seems like pretty on the edge. Yeah.
Yeah. That was my other question, is the support stuff, right? If you don't have a crane big enough that can, has a ship big enough to support the crane when you're way offshore, then that might be your bottleneck.
Right. And it's going to be cheaper to make many more smaller ones than one large one. That economics will cross here pretty soon.
So moving on to gearboxes, and this is obviously the same topic here. So the National Renewable Energy Laboratory, the NREL, has done some interesting research on gearbox failures. And they're saying basically that a lot of hardworking components, just like these, don't quite make it to their entire 20-year lifespan. And gearboxes specifically often suffer from what they call white etch, which is some cracking in the roller bearings inside the gearbox. Alan, what stuck out to you as far as this article about gearboxes and some of the failure modes?
Well, the failure modes were interesting because they didn't really have a handle on what was causing it. And one of the first engineering tasks you need to do is be able to recreate and figure out what the source of the issue is. So what they ended up doing was making a little test set, essentially, that could, in theory, recreate these kinds of fractures in the bearings. And one of the interesting things that came out of it was the different kinds of lubricants that are used sometimes allow the two interfacing surfaces that should be rolling against one another to slip and to slide. And in that sliding effort, you can create these stress cracks. But if you can imagine, it's like in an automobile. If I'm going to go down and put new oil in my engine, I have a variety of choices, and they're not all the same. They're close to the same, but the additives will change, and whether it's synthetic or it's real oil pumped out of the ground will change also. So you don't think about that as having an effect on the performance of the mechanical system, but as they're finding in the research that they're doing, those particular lubricants have a big influence on whether cracks develop. And I wouldn't have pick that as the place of the source of the issue. So it's really fascinating that as they delve deeper and deeper and deeper into this thing, it's not really the bearings themselves. It's all the things we use, the fluids we use to keep them operating that may be inducing failures. That's an interesting feature. And Rosemary is more the mechanical person. I'm an electrical person. But Rosemary, did you pick that same sort of thing out of the discussion?
When you think about a gearbox and bearings, and you think, these are things that we've been using for at least hundreds of years, right? In other applications. So you might wonder why is this such a big deal for wind turbines? And I think it's like anything that you put in a wind turbine has this extreme operating environment that's really different to what it had in its previous life, and where you get your the lifetime data for a bearing or whatever. It's based on different operating environment, and it's not going to apply to your thing that you're putting in a wind turbine. And I saw that with everything that I put in the blade for the heating systems. I was always taking things off the shelf as much as possible. And people think, well, why do we need to test this? It's got a warranty, it's got a design lifetime, but you put it in a wind turbine with all these vibrations, constant fatigue, just all sorts of fatigue in different frequencies. So things break, and it has taken some time to kind of figure that out for wind. And then the second thing that's different is just how hard it is to replace. You've got your gearbox in your car, and if you stuff up and choose the wrong lube, I mean, the consequence is that you take it to a shop and get it replaced, and that feels painful. You don't want to pay for that, but compare that to getting a crane out to lift the top off your nacelle and drag the whole gearbox out of a wind turbine. I mean, you can see that it's going to be really appealing for a wind turbine operator to get some heads up that something might be wrong, and give them a chance to do some preventative maintenance because the consequence is so high. So yeah, I think that's the main difference with the wind turbine gearboxes.
Well, is this another one of those items that's falling into an arbitrary 20-year lifespan? Like 20 years is a really round number. Like it, just like when we say, oh, it should be 100 or 100 years or 10 years or 20 years, they're all just round arbitrary numbers. Like, is it arbitrary? Is that why we're not meeting any of these 20-year lifespans? I mean, could you really design a blade or this or that to make it 20 years, or is it just wishful thinking?
Some components you can design to whatever life you like, and some components you can't. So bearings are one of the things where they are legitimately struggling to get the lifetime as long as they'd like. But in general, you want the life as long as possible. That, when you're calculating the levelized cost of energy, you're dividing by the number of years of lifetime. So the bigger that number, then the cheaper your energy is, and the easier to get financing, the more profit you're going to make. So definitely we see a trend towards increasing lifetimes. And for a blade or a tower, you can get there by just adding more material to, get the extra life, the extra fatigue strength. But for some components, and I understand that gearboxes and bearings are still at the stage where, like, actually they're trying their hardest to make them last as long as they can. It's not a matter of, we could design a 50-year gearbox if we wanted to. I don't think anyone can do that.
Alan, is it going to take like new higher tech materials, like harder alloys, or is it just, is there something else that maybe we're missing?
I think the issue right now is that the loads and the forces are growing faster than the engineers can keep up with the failure modes. So as we push into 12, 13, 15, 16, 20 megawatt machines, that means you're talking about more mass, more loads, more forces, that you're getting to the point of you're going to get different kind of failure modes in the bearings that you may have had on the 1 megawatt machine. And so in the sort of the maintenance side, maintenance is always playing catch up to the design engineers. The design engineers put out this product and off it goes, and kind of look to the next machine. That's what their job involves. But it's the technicians that have to live with the results of that. And the technicians find out 5, 6, 7, 8 years later that initial concept, that initial analysis may not prove out just because. And the engineers, as you push higher and higher, the same thing goes on with blades. As you keep pushing higher and higher and higher, you're getting to some places you've never been. And so you're automatically going to have failure modes you never thought of. Guaranteed. And airplanes, we see it. On wind turbines, we're going to see it. I guess the question is, at what point do the economics get so bad that you start taking steps back? Like, you could make a 20 megawatt machine, but you really can't design bearings for it. So there may be limitations like the bearings where we just don't do it. We just say, all right, 12 is a really good number for us, and 12 megawatts is a sweet spot. We're going to stay there for a while, because wind turbines haven't stayed anywhere long enough to really prove out a lifespan. We'd be just continually getting bigger and bigger and bigger.
Well, and that's a good segue into one of the companies that I found doing research for this, which is Poseidon Systems. They have a number of different sensors for gearboxes. One of them is their Trident wear debris monitor. And they are basically looking for metallic debris. So and they can classify it, whether it's ferrous or non-ferrous. And I guess that can give operators an idea of where that those little flecks of metal are coming from. I mean, is that sort of how something like that would work?
I do understand it's trying to be an early warning system for them, so they know, where we've detected something strange, and you better get in there and do some maintenance before, one of your bearings just shatters or whatever. That's my interpretation of it. So I think that there's also other ways of doing predictive maintenance where, you know, they're watching for the vibrational frequency, and they can, you know, pick out, oh, one of your bearings is cracked or is rounded or whatever. And if you're looking at the vibrations, then you can get in there and replace that before it gets to the point where the whole thing is just stuffed and you've got to totally remove it. So I'm assuming it's the same kind of principle of, you know, looking for some early tell that something bad is about to happen.
Yeah, I mean, Alan, they do a lot of this stuff on aircraft where you have an idea of, hey, we need to replace this well before it has a chance to fail. And I'm sure a lot of that's already going on with wind turbines. But I mean, is that maybe the best that we can hope for in the future? Like if something, like you said, can't be designed to withstand 20 years of rigors, like, hey, let's just, do they even then maybe design components to be a little more easily replaced or more often replaced? Like, hey, let's not spend X amount of dollars trying to make this bulletproof when we know it can't be. Maybe let's go a little cheaper and just we'll replace that gear every 5 years instead of trying to make it so expensive that it can make it 8. Would that be a reasonable solution?
It's reasonable on aircraft because aircraft tend to be in places where you can repair them. They're on the ground. They're usually in a hangar and it's dry. And so making those swap outs does happen, and it's pretty regular. On a wind turbine, you really can't do that very easily. And that's the big difference. On a jet engine, I'll give you an example on jet engines and helicopter engines for that matter, is that they have monitoring systems, vibration monitoring systems. So they're constantly looking at the acoustic signature of the motor to make sure everything is working the way it should. And if you see something odd happen, the engine has a data system, and it'll transmit data out after a flight to the manufacturer that says, hey, this particular engine is unusual. Somebody needs to be looking at this thing. And they also create fleet data from that. So a Pratt & Whitney will be able to see the whole fleet of airplane, or a substantial part of them, to see how the whole things are performing and where you may have unique situations because of the operating environment. That's been going on in aerospace for 20 years at least. And the wind turbine side, you don't see that as much, weirdly to say. I don't think the OEMs are necessarily always getting data back. And it's getting to the point where the size of the wind turbines are getting so massive, and you're pushing the limits of materials that, as an OEM, part of the agreement on which I'm going to sell you this wind turbine is I get to have the data back. I get to see how my wind turbine is performing, because I need to know what is coming out of the factory is actually going to do what we say it's going to do. And that's the only way you're going to know is to accumulate data.
Yeah, so I think that we see a trend now towards, because you're absolutely spot on when you say how hard it is to get the data once you've sold a turbine. And so a lot of manufacturers are now purposely getting into service so that they can get that data. Like maybe the service part of the business isn't super profitable on its own, but the data that they get is so valuable that they want it anyway. So I think it's going to be a big thing in the future. And we do see the industry changing as it learns the operating environment, because, you know, if you think about it, you're trying to test for a 20, 30 year lifetime, but you got to accelerate that, right? And do it in 6 months or less than a year anyway. And some things are easier to test a lifetime than others. So, you know, they have a pretty good method for blade structures. It's not perfect, but, you know, they can excite it, wobble it, get the right number of movements that they would see in a lifetime and test it that way. But something like a bearing, you know, if you're actually getting enough revolutions, then either you've got to make them so fast that they're going to heat up in a way that they wouldn't in operation. Same, anything that's got gravity loading, it's incredibly hard to accelerate that in a realistic way. So some of it you need actual calendar years to test an actual calendar year for some things. And, you know, we see wind turbines don't park anymore the way that they used to. They're mostly idle. And that I believe that's mainly because that's a lot easier on the bearings to not sit there in the one location, because that gives them flat spots. So I think we'll see some improvements just the longer the industry has been around, with a lot of turbines around.
All right, so moving on into hydrogen. So Acciona is planning to build a floating wind and solar hydrogen complex. So the Spanish developer has got some government funding, and it's going to be called the Ocean H2. So Rosemary, you're our green or blue or whatever colored of the day sort of hydrogen expert. How excited are you about this floating hybrid farm? Is this, I mean, this is your dream.
Close to a zero excited, I would say.
Okay.
I'm sorry. I mean, yeah, it's always cool to see ambitious things, but I don't understand offshore hydrogen, and I don't understand offshore solar. I understand offshore wind because you go offshore, the wind resource gets much better. So there's a reason to be there. And you pay the price for it in terms of really expensive installation and expensive maintenance. And for any new technology that you're developing, in the early days, you're going to be out there a lot figuring out why it's not working the way that you thought it was going to, right? So for solar, that's quite mature, so maybe they're ready to go offshore. But why? I mean, they say, I was reading a bit into this because I actually didn't even know that offshore solar was a thing until I saw this article. And, so some countries are filling up their onshore opportunities for solar. They want to go offshore. I just can't imagine that it's worth the headache, but okay, that's a thing. But then hydrogen, I mean, it's really, electrolyzer technology isn't brand new, but it is brand new that we're going to be using them in this way with a wind turbine. Why aren't we doing it onshore first to figure out if this is a good idea, and even to see if the markets are there to make their business case make sense? I just think that we're so far jumping the gun by so far to put offshore hydrogen wind turbine hybrids, and then secondly to add solar into it. I just think that this is going to be so much more complicated than it needs to be. That's my opinion on that one.
Rosemary, you think it's the effect of being in international waters and taxation that essentially there is no governmental control over it? And in a sense, I mean, you were really creating energy from the sea, so to speak. And if you turn it into hydrogen, you have an open market to walk into any place that the highest selling market and just basically drive a ship to wherever they're going to pay you the most for it. It sounds like that's what this is driving towards, that it's more economic than engineering related.
Sailing towards. That's what this is sailing towards.
Sailing, yeah.
I mean, that might be true. And there is also, so I shouldn't be so dismissive of the wind hydrogen combo, because there are some kind of synergies for putting it both offshore, because you don't need then to put a big subsea cable in. You can just get ships to go, or a pipeline. So there's something there. It's not just a matter of complicating it for no reason. And maybe you're right. That's, that sounds plausible. But I just don't see why you need to do that now. Get your technology working. I just, in the offshore wind industry, anything that you can do onshore, you do it onshore. Always. It's just the cost just goes through the roof when you everything you add to it adds maintenance cost, and times it by 10 because it's offshore. It's just, I don't understand it. And then I did wonder with this project if it's more for the headline, generating concept, get all of the cool podcasters to talk about it because it's so crazy. That's probably the most, I don't know, the most sensible interpretation that I can make of this project.
Well, it says that the total cost of the project is 7.25 million, or 6 million euros, which doesn't seem very big. Either it's a really tiny experimental thing, or it's, I don't know, they're getting it manufactured by IKEA or something. I don't know. But maybe it's not very big.
Maybe if the wind turbine was going to be installed anyway, maybe the incremental cost to put an electrolyzer and a solar panel next to it is about 7 million. That sounds about right to me. That's what I would be asking for if you wanted me to take an existing wind turbine and put a solar panel and an electrolyzer offshore. I think I could get something done with that much money, but yeah.
Well, I think there's going to be fewer problems of Elon Musk getting to Mars than this thing going together. There's just fewer problems to solve. Because the number of problems you have to solve to get to Mars is just like mass, right? Just build something bigger. And this thing, you got so many moving parts. You got wind, you got solar, you got electrolyzers, you got a ship involved. There's just so many moving pieces from an engineering standpoint. You have each one of those problems is very difficult to solve, and you stack them all together at the same time and try to make a nickel on the project. That's really hard.
And it's floating wind, right? So that also is not mature yet. I mean, I think it's got potential, but to solve all those problems at once, I feel sorry for the project manager, and he's trying to bring that together on a schedule. It's going to be a tough job.
All right, so moving on, there's a interesting graphic called the Clean Hydrogen Ladder by Michael Liebrich. And as he describes it, it's his attempt, quote, to put use cases for clean hydrogen to some sort of merit order. So at the top, there's unavoidable. These are things like fertilizer, hydrogenation, methanol, hydrocracking. And at the bottom of the ladder are things that are uncompetitive, like metro trains and buses, urban delivery, 2- and 3-wheelers, power system balancing. And then somewhere in the middle, there are things like long haul, medium haul, short haul aviation, ferries, trucks and coaches, stuff like that. So Rosemary, what is the story of this ladder? What is it mostly trying to convey?
Yeah, so I mean, I really love this ladder because I think it's just such a really clever way to communicate hydrogen. Because I mean, if you read the article, you can see a bit further down, it's got this graphic of a Swiss Army knife with about 1,000 different attachments, and it's like, yeah, in theory, you could carry this knife around with you and do everything that you wanted to do with it, but in reality, it's never, it's not the best tool for many jobs, so you wouldn't. And people talk about hydrogen a bit like that. You're like, oh, it could do anything, and they're right that it could do anything, but it won't, because there's alternatives that make more sense. So in this ladder, it's been done in a really rigorous way, where you take every single thing that people talk about hydrogen being able to do, and then look at what else could we do it with instead, and does that make a lot more sense? So yeah, like you said, on the top, you've got things that hydrogen is already doing. We already have a lot of hydrogen getting made. It's all very, very dirty. And yeah, so that includes especially fertilizer. It's probably the largest one. And then at the bottom, you see of the least likely technologies, you've got fuel cell passenger cars and power system balancing, which I think is the things that people, maybe non-engineers, think are the main things that hydrogen is going to do. So to see them right at the bottom is really interesting.
Well, I think this is an economic ladder. That's the way I looked at it. Like it's determining whether it's a cost-related issue. It's not an engineering challenge issue so much as, can you economically make this work versus all the other alternatives? And I think as a bigger picture on the engineering side is that the economics kind of get tossed by the wayside because engineers don't tend to think about the money part of it too much. If it's cool, I'm going to buy the Tesla, whether it is the most economical way to get me around town or not, seems to be secondary to the discussion. But ultimately, the economy is going to be the bigger driver in the financing of these things. And things that are economical are going to pick up hydrogen. Engineering pieces that won't, like making a lawnmower run on hydrogen, doesn't make any sense at all. It's just not going to happen. And I think that's the way these get filtered out over time, is that if you can make money on it, they're going to stay. If you can't, it's going to go away. And hydrogen's going to find its sweet spot at some point, particularly in these large industrial things. I think that is the sweet spot for hydrogen right now, is large industrial places which need hydrogen, fertilizer being one of those, is where if you had a wind turbine solar plant and an electrolyzer and you're creating that hydrogen right next door and it makes your operations more economical, slam dunk, all the bean counters are going to say, go ahead and do it. But if you're talking about generating hydrogen from natural gas and shipping it across the country, makes no economic sense, won't happen.
Rosemary, I want to use that as sort of a transition into some of these different methods of creating hydrogen. So a couple articles have come out a little bit critical of blue hydrogen. Can you tell us, as I made a little joke earlier, what are the different colors, quote unquote, of hydrogen for those who aren't as savvy as you are?
Yeah. I mean, there's no definitive word, actually. I keep on seeing people come up with different colors for different things. But the way that, some of them are definitely agreed upon. So green hydrogen is made from electricity, from renewable sources, although there's no color for hydrogen made from non-renewable electricity. So, you feel free to make up your own color.
Brown. I say brown, dirtiest color.
No, brown hydrogen's from brown coal.
Dang it.
From gasification of brown coal. So that one's taken. And then blue hydrogen is from steam methane reformer to make hydrogen, and then you put carbon capture on it. But it's usually used for just any kind of fossil fuel hydrogen that has carbon capture added to it. And that's been proposed as, a second pathway to decarbonisation. And so I think I'll say a little bit about why so many engineers are so passionate about hydrogen and this hydrogen ladder, including me, and about the economics, because it's not just like the cost of it that's the issue. It's how fast we can get to decarbonisation in general, right? And hydrogen, it converts, if you use electricity to make hydrogen and then back to electricity again, which is what you're doing if you're using it to balance a power grid or in a passenger car, because a hydrogen fuel cell car is an electric car. It's really inefficient. You get 1/3 of the electricity back that you put into it. So you can imagine if you scale that up and you have like lots of power system balancing, lots of hydrogen fuel cell passenger cars, you need 3 times as many wind turbines or solar panels as you would need if you were able to just use that electricity directly or from a battery. So, we can expand our solar and wind industry a lot, but not infinitely. 3 times as many is a big deal. And there's other things that we could be doing, decarbonizing with that green electricity. So that's why a lot of engineers get really passionate about the economics of it, because, it's a handbrake on our energy transition. If we start using hydrogen willy-nilly, then, we're missing out on opportunities to do something else with it. So then enter blue hydrogen, which is a separate pathway. It legitimately is a separate pathway to, rolling out hydrogen without cannibalizing, green renewable electricity in general. So it sounds really nice. You've got your fossil fuel hydrogen manufacturing, which is the way that it's done. 98% of the hydrogen that's made today is from fossil fuel source with no carbon capture. Add carbon capture, now you can call it clean hydrogen, and it's not taking renewable electricity that would have done something else, and we can use it to expand all of these amazing things in a Swiss Army knife of hydrogen. It's perfect. And so then comes along this study, which is the first peer-reviewed one that's rigorously looked at the whole emissions chain of blue hydrogen, and found, hey, it's not so appealing as it sounds. And, I think calling it clean hydrogen is a real misnomer.
So what was misleading about that idea that blue hydrogen is just like super duper clean? Like, where does it go wrong?
Yeah, so it sounds really simple. You just, shove carbon capture onto the steam methane reformer and suck out all the carbon. But in reality, you can capture as much carbon as you want, basically, but the economics kind of set a limit. It's hard to go much above 90% capture for just the steam methane part of it. And then you also need heat and pressure, which usually comes from gas as well. And that the emissions are much lower concentration out the flue gases. So that's harder to capture. So this report included not just that part of it, but also the upstream emissions. So, in the natural gas extraction and transporting, there's a lot of losses. There's leakage. And this report in their main baseline scenario assumed 3.5% leakage of that methane, which is on the high side, but they did also do a sensitivity analysis right down to kind of like the lowest estimates of about 1.5%, and they still get roughly the same conclusion. So they included all of that, and then the fact that you need a lot more gas to make hydrogen than to get energy from hydrogen than if you just burned that gas directly. If you wanted, a certain amount of energy, you you can burn gas to make the heat, to make the electricity, or you can use, like 3 times as much and get it from hydrogen, via hydrogen. So then you're multiplying all of the upstream emissions, and you get to the point where actually blue hydrogen, for the same amount of electricity out, blue hydrogen has more CO2 emissions than just burning the gas directly. So as a transition fuel, you're not actually making any improvement on your emissions outcomes. So, can we call it clean when it's dirtier than what we're replacing? And can you call it a transition when it's a step away from our carbon emission targets? It's, that's the real interesting thing about this study. It's like, does blue hydrogen actually do any of the things that we've been told that it's going to do?
That actually reminds me a little bit of the ethanol discussion here in the US from 20 years ago. Like the government subsidized ethanol from corn quite a bit. It was added to gasoline and like 85% gasoline, 15% ethanol mix. But when you started to really break down the economics of it, it didn't seem like it made a lot of sense, both from the cost benefit and also just the amount of trucking and all that other stuff. It seemed like it was contributing more. And I don't have those numbers, but I remember that conversation. Alan, I mean, is that a decent analogy, or am I way off?
Yeah, I think that's a pretty good analogy. And I think I look at it a little bit differently than Rosemary in this particular case. There's a lot of technologies that may not be ideal. I think if you're talking about the world and an industrial economy and trying to get to a cleaner environment, one of those transitions you're going to have to make in all these countries is you need to get economic development up. You need to get the economies growing faster. You need to bring essentially everybody out of poverty into somewhat of a term, sort of quasi middle class sort of status, at least. That's your fastest way to bring down emissions, is that once we get society on some at least moderate basis, then we can attack these other problems. But if we don't attack the sort of the poverty problem first, we're going to have a much more difficult time to getting to a really a carbon neutral, carbon reduced society. So in the transition, I think we have to kind of suck it up a little bit. And I think one of the keys that has happened recently is, like in the United States in the Paris Accords, one of the things that happened with the Paris Accords, everybody went off and there's all this clapping and cheering and stuff that has happened. But the United States is the one who actually reduced emissions. And we did it in an unnatural way, or in a way that wouldn't have been approved by the Paris Accords, so to speak, or wouldn't have been looked upon kindly. But when we made that sort of natural gas transition, we did reduce the amount of emissions. That's not going to last forever, but did it help stabilize the economy? In some parts that it did. And I think then the United States can do those sort of next generation things in terms of energy development. So I'm willing to suffer a little while to bring up the world economy, to then really push down the carbon emissions, because we'll be at a better place to go do it. So it's sort of, let's get the economies working first, then let's attack carbon. They both need to be solved. It's a question of which do you do first, and how do you get to the end result for both of them sooner.
I'm on board with that, and I'm also on board with the idea that green hydrogen is going to be really it's going to take some time to scale up to the point that it needs to, and so this is it is a legitimate second pathway. Doesn't look like it's super. It's not a large step, or maybe any step towards decarbonization, but it is a step towards getting these, industries swapped over to hydrogen. So I don't have so much of a problem if it sticks to applications that are going to make sense for hydrogen in the long term. And I would really love to see it done, within a framework that made sense as well. Because at the moment, it is really similar to that ethanol thing, where it's the government saying, put ethanol in fuel, or the government saying blue hydrogen is the go. I would much rather see it done with a carbon tax, like it's I wish that people in countries like ours are never going to, see fulfilled, but that would be the way to do it. Then you can sensibly choose the decarbonization pathway that has the least economic pain. So I think that's the best way to, get sensible economic outcomes. But I also don't believe it'll ever happen in Australia. So.
Yeah, I don't know if the economics of that really work out. I think that's the reason why the United States has a big problem with carbon taxes, is that economically, we're not sure that's the best answer to get to the final solution. And that's the debate. Do you artificially skew the marketplace so much that you force decisions, you force engineering to go in a particular way? And we saw that during the last economic collapse in 2008 with the government taking over General Motors, essentially, and telling them they're going to build an electric vehicle. That vehicle went absolutely nowhere. Unfortunately, went absolutely nowhere. And it was not the right thing at the right time. And those sort of edicted, government mandated engineering bits never seemed to get to the better part. Tesla was off there making cars, and they didn't get wrapped up in that. They're going to be the winner. GM is not going to necessarily be the winner in that. And the government didn't really help it. So in some cases, I think society in general, people like us that say, hey, cleaner is better, are going to be making the decisions. And that's probably a better way and a faster way to get to the ideal than letting the governments force it on us.
So last story for today, this one's in Rosemary's neck of the woods. And this is just sort of that conversation that's going to be happening in an increasing amount, is of people who have done work in fossil fuel industries their whole life, as they see those industries start to hit their sunset. So this interesting story out of Australia about Hunter Valley, which is supported by coal, they're starting to see their end and starting to talk about what's next for our children and grandchildren in this area. And one of the interesting technologies that's popping up in that area is MGA thermal. They have these sort of alloy bricks that are made of various metals that essentially they can heat up if they have extra energy from the grid, whether it's heat or extra electricity. They can heat these bricks up, stores that energy as heat, and then they can use it to either release that later as steam or to power some sort of industrial process using the heat. Rosemary, I mean, is this just a conversation that we're going to continue to have, where older generations are seeing their line of work, like you said, fade into the sunset in favor of new technologies? And how are these people going to get sort of moved on and their next of kin on board with some of these new facilities that'll be built?
Yeah, so I don't know if I've mentioned it on this podcast before, but I have been noticing as I climb turbines every now and then with technicians, and I meet some interesting people there, and I'm always asking them about how did they get into that line of work. And one time when I was climbing in New Brunswick, I believe that was traditionally a really strong mining area. And I climbed with this guy. He's like, I was a coal miner, my dad was a coal miner, my granddad was a coal miner. Gee, it's really nice to be, above the ground as a wind turbine technician. I love this job. And so, that's an area where they've been able to at least start to make that transition away from the coal mining jobs and into clean energy. And also, it highlighted for me that, it's not like magical skills that are needed in clean energy. It's really similar things to what are needed in mining and, coal power plant. So my most recent GWO training, there was a guy who was an apprentice electrician who wanted to work on wind turbines to get away from ridiculous inner city housing prices. There was a guy who used to repair aircraft who was now wanting to repair wind turbine blades because, COVID shutdown has, grounded a lot of aeroplanes. All sorts of tradespeople from all sorts of backgrounds are getting jobs in wind. And then this company is another example of, they're taking really normal kind of skill sets. They've got this cool technology with cool materials technology. So it is pretty high tech, but, they've got these hot bricks that they want to heat up. It's not the only kind of thermal energy storage that we see. But what I really liked about their system is, you can do it anywhere, and you can even retrofit a coal power plant that's been, decommissioned. You can put these hot bricks in there and use the turbine from the coal power plant to get your to make electricity from it. So it's from a university in this traditional coal area where they are thinking about the future and what else that we could do, because the writing's on the wall for Australian coal mining. At least 95% of it is exported to countries that have zero emissions targets. So it doesn't matter what our domestic policies are, things are going to change. And so I was just really excited to see, and then there's a ton more. It's not just this one project. There's so many things happening in this region of people who are, really thinking ahead. What are the jobs going to be? What are the opportunities going to be? And for me, I think these traditional coal areas are a really good place to put in, go back to manufacturing. These areas they used to have really cheap electricity, used to manufacture a lot of steel, a lot of aluminium, and then that dropped away as electricity prices rose in Australia. But there's a huge opportunity in the future for renewables to bring, clean and cheap electricity, get those industries back. I think we're starting to see people realize energy transition is an opportunity even for the communities that you might think are going to suffer from it.
All right, well, that's going to do it for today's episode of the Uptime Wind Energy Podcast. Thanks again for listening. Be sure to subscribe to the show, whether you listen on iTunes, Spotify, Stitcher, or YouTube, and check out the show notes where you'll find Rosemary's awesome YouTube channel, as well as Uptime Tech News, our weekly update for all things wind energy, technology, stocks, business, what have you. So we'll see you here next week on the Uptime Wind Energy Podcast. Operating a profitable wind farm is all about mitigating costs, minimizing risks, and being efficient with maintenance, repairs, and upgrades. It's incredibly expensive to send a team of rope access technicians up tower to make even simple repairs. We also know how costly lightning damage can be, requiring inspection, repairs, and downtime for even minor lightning strikes. Maximize the time efficiency of your techs and prevent future lightning damage by installing our Strike Tape LPS upgrade the next time your crews are going up on ropes. Learn more in today's show notes or visit us on the web at weatherguardwind.com.